In this segment, what we're going to do is we're going to talk about differentiation of discrete data. And we're going to look at an example by using Newton's divide difference polynomial. So we're going to use the Newton's divide difference polynomial to be able to calculate the derivative of a function which is given at discrete data points. So let's go and look at what example we are looking for. So let's suppose if you have an aircraft landing and you are given the times and the location, and what we want to be able to do is we want to be able to find out what the velocity will be at a particular time. So let's suppose somebody is telling you that, hey, this is time in seconds and x in meters, and says that, hey, at different times, this is what we are finding during emergency landing, what is happening, at what location the aircraft is at different times, 2.5. So at 0, it's at location 20, at 0.4, it's at location 71, at 1 is 110, then 161 at 1.75, and 178 at 2.5. Can you go ahead and find out what the velocity at 1.75 is? So you can very well see that if the location is given to us, the velocity will be simply the derivative of the function x with respect to time. And that's what we want to be able to calculate. We want to be able to calculate what dx by dt is at 1.75. That's what that means. And what we're going to do is we're going to use the Newton divide difference polynomial method to do so. And so if we're calculating 1.75, so let's suppose we're going to use second order polynomial. Second order Newton's divide difference polynomial. So if you're going to use second order divide difference polynomial, we've got to choose 3 points. And since this is 1.75, we'll choose 1, 1.75, and 2.5. Those are the 3 points which we will choose for doing the interpolation and then differentiating it with respect to time to be able to calculate what the velocity at 1.75 is. So we are choosing 3 points. So let's suppose we call t naught to be 1. The corresponding value of x, which we are getting here, is 110. Then t1 is 1.75. And the corresponding value of x is 161. T2 is 2.5. And the value of x2 is 178. So we got these 3 data points which you're going to choose to use second order polynomial, Newton's divide difference polynomial, to be able to calculate the derivative of the second order polynomial to calculate the velocity at 1.75. So as we know that the second order divide difference polynomial will look like this. f2 of t will turn out to be f of the divided difference at t naught. So it will be t naught here, then f at t1 comma t naught, or I should call t naught comma t1, t naught comma t1 times t minus t naught plus the divided difference now of t naught, t1, t2 times t minus t naught times t minus t1. But I'm interested in calculating the derivative of this. So f2 prime of t, this will be 0 because it's a constant. And here I'll get a 1. So it will be f of the divide difference at t naught and t1. T naught and t1 plus f at t naught, t1, t2. And what I'm going to do is, rather than expand this, I'm going to use the derivative of a product, and I'll get t minus t naught from one and t minus t1 from the other one, which basically tells you that you don't have to do any kind of symbolic manipulation to be able to calculate what the derivative of the function is if you know how to expand the derivative without having to do so. So let's go and see what we need to do in order to be able to get this. So we know that the divided difference t naught and t1 will be nothing but the value of the velocity at t1 minus the value of the velocity at t naught divided by t1 minus t naught. That's how that is defined. So this one will turn out to be equal to not velocity but location. And what is the location at T1 is 161. The location at T0 is 110 divided by T1 minus T0, which is 1.75 minus 1, and this number here turns out to be 68. So that's what we get for the divide difference of the of f with T0 and T1. So let's go and calculate what f of T0 comma T1 comma T2 is, what that is. So f of T0 comma T1 comma T2 will be nothing but the location x2 minus T1 divided by T2 minus T1. So it's the divided difference between T2 and T1 minus the divided difference between T1 and T0 divided by T2 minus T0. So that's what you get there. So if we do the substitution now, we get this as the value of the divided difference, 178 minus 161, because that's the value of x at those points, 2.5 minus 1.75. That's what we get there. Minus 161 minus 110 divided by 1.75 minus 1 divided by the difference between T2 and T1, which turns out to be this. And this number here turns out to be minus 30.22. So having calculated these divided differences, that means that our velocity expression, which we have, will be approximately equal to the divided difference between T0, T1, which is 68, plus this quantity here, which is minus 30.22, times whatever we have, which we calculated, which is T minus T0 plus T minus T1. So we get here 68 plus minus 30.22. T is T0 is 1, and T1 is 1.75. So that's what we get as the expression for the velocity now, and this is valid between the points 1 and 2.5. Now we are asked to calculate what the velocity is at 1.75, so all we have to do is to substitute 1.75 in there. We get this 1.75 minus 1 plus 1.75 minus 1.75 here, and this value here turns out to be 45.33 meters per second. So that's how we are using the divide difference polynomial method to develop the derivatives of functions which are given at discrete data points, and that's an example of that. And that's the end of this segment.